Today, we're going to talk about another concept in statistics called Simpson's paradox. Have you ever heard of this, Wade?
No. Do you have an example?
Yeah, for sure. So, Simpson's paradox is actually an extreme case of confounding. So, this is another example of why observational studies are not ideal. This is something that could happen in observational studies that can actually be very scary. And you asked for an example. So I'm going to give probably the most classic example of Simpson's paradox, which actually has to do with Berkeley admissions from 1973.
So this is a data set we have.
Yes, this is a data set we have, and I actually have the research paper here. So back in 1973, Berkeley actually released their admissions to graduate school for that year. And they looked at whether students identified as male and female, and then they calculated the percentage of admission rates for those students. So, Wade, you have our data set pulled up.
Yeah.
Let's go ahead. I'm going to put that right there. Let's go ahead and look at the overall admission rate. So, again, Berkeley looked at men and women, and this was what percentages of them were admitted to graduate school. So, I'm going to go ahead and look at the overall admissions rate. So, what do you see, Wade, for the men?
So 44.3% of men were admitted to Berkeley out of all of those who applied.
That looks good. And then what about for the women?
For women, only 34.6%.
So here is the problem, 34.6%. So back in 1973, when this data was released, people automatically jumped to the conclusion of saying, oh my gosh, Berkeley is biased against women. Look at these numbers. This was a statistically significant difference. It was big enough to cause um, a scare. People thought, oh my gosh, why are 43% of men getting admitted, whereas only 34.6% of women were getting admitted? So
So that's
before
bad. Like,
that's
what would a statistician do to evaluate this or dive into this more?
yeah, so that's a great question. So if I was looking at this data as a statistician, as someone who knows about experimental design, I would first ask myself, okay, can I say, I'm going to think back to our diagrams, can I say that being male is more likely to cause you to get into Berkeley, to have causes a higher admission rate? And we need to decide, what type of study was this? So, Wade, was this an experiment where the researcher was deciding who was in the treatment or control group, or was it more of an observational study?
So the researchers didn't have any impact on whether or not someone applied. So they just observed what happened. So an observational study.
Yes, and we know observational studies can be problematic. There could be a confounder. There could be actually a third variable, which we call a confounder, which is the difference between men and women, in this case, our treatment and control groups, that is associated with the men, male applicants, and also associated with a higher admission rate. So if I was answering the question, is Berkeley biased? Does being a man give you a higher admission rate, cause you to have a higher admission rate? I would say I'm not sure. There actually could be a confounder. So with this data, what they did, one tool to kind of adjust for confounding variables is to stratify. And basically, what that means is that we're going to look at different categories instead of the overall results.
So what would be a category you might look at?
So, what they decided actually was, how about we go ahead and look at the majors? Let's just see what are the different majors and what's going on with that. So, Wade, in this data set, what were the majors that they gave?
So they only gave us anonymized majors, but they gave us the top six majors that people applied to as letters A, B, C, D, E, and F.
Okay, so we saw something like this. We saw letters A, B, C, D, E, and F.
And we don't know what these majors are, but we know that A is the most populated major and B is the second most populated major.
Got it. And so they decided the idea of stratification is to basically look at the majors individually. So I'm going to say, let's look at the men that applied to major A and the women that applied to major A. Let's ignore the overalls for now. So let's see, what are those percentages? For men, what percent of men were admitted to major A?
So the number of men who were, or the percentage of men who were admitted to major A, only looking at major A, is 72.5% of men.
All right. And then what about the women?
The women, 82.4% of women who applied to major A were admitted.
2.4%. Okay, so we see our paradox here, right? This is confusing because if we look at Major A is actually favoring the women, right? There's a higher percentage of women admitted to Major A. So how is this possible? This is Simpson's paradox. It's crazy because overall we see the higher percentage goes to the men. So oftentimes people will think like, did we mess up the data? Did we do something wrong? But this is Simpson's paradox in a nutshell. So let's look at Major B. So right now I'm like, okay, well if I compare these groups are more alike. We're looking at Major A and Major A for men and women. Let's do the same for Major B.
For Major B, the number of men admitted to Major B was 63.0%.
All right, 63%.
And then the number of women who were admitted to Major B was 68%.
So again, we see the same thing as Major A. In Major B, we see the opposite of the overall results. There's a higher percentage of women that were admitted. So we could keep going and look at all these different majors, but what they saw actually when they stratified or looked at the individual groups, they saw that most individual majors either kind of favored the women or were about equal. So how did this happen? How did we get these crazy overall results? And what happened that semester was that they saw that a lot of men were applying to these majors A and B specifically, which had over 50% admission to the majors. So majors A and B, they actually classified as these easy to get into majors, whereas majors C through F were a lot harder to get into. They had admission rates less than 50%. So that year in 1973, for some reason, men were more likely to apply to majors A and B. It seemed like all the men were applying to these easier to get into majors, and most of the women were applying to these harder to get into majors. So the confounder was this idea of easy majors. Easy majors were more likely to have men in them, and easy majors are going to cause a higher admission rate because they're easier to get into. So the conclusion here is actually the opposite of what we saw overall. Berkeley was not biased against women. It just looked like that because of this confounder. The easy majors was making it look like the men had the higher admission rate.
And when we dive into examples, we'll look at this data set and we'll fill out this full table for us.
Yes,
So we can really
exactly.
see it.
And we have this data set for you all, so you're going to be able to play around with it and kind of see this for yourself. But this is a takeaway from this video is that Simpson's paradox can occur in observational studies, and it's extra dangerous because if we don't take into account the majors, we actually see the opposite of what's true. So you can imagine in certain situations, especially something high stakes like this, that's really scary. Berkeley could have gotten in big trouble for this when really it was the confounder that was mixing up our results. So in observational studies, we never want to look at overall results and conclude causation. Correlation doesn't imply causation because of 3 reasons. The first reason is that our treatment and control groups are bound to be different in observational studies, right? In this case, in this observational study, men and women were different in terms of major that year. Second reason we don't want to look at these overall results and include causation is because confounders can mix up our results. We have to be aware of confounders with observational studies. And the third reason, I guess the scariest reason, is that sometimes even Simpson's paradox can occur. And Simpson's paradox can give us the opposite of what is actually true. So we will dive more into this data set in the future, but that is kind of an overview of Simpson's paradox and the dangers of it.